Well, keep asking me that. Don't stop asking me that. I just so happened that the button was already hit today. So yeah. Oh, if it's something that's mono substituted, all that means is that it has one substituent on it. Right. So we put something on here like a chlorine, then the name is simply chlorobenzene. Right. So the benzene is the parent. Right. If you put a different substituent on there, something like a nitro group, then it becomes nitrobenzene. If it's mono substituted, right? You can put if you put an aldehyde here, let's just do that because that's a common functional group. Then the name, instead of benzene being the parent, we call it benz aldehyde. Right. So naming benzene compounds, normally the benzene ring is the parent. There are some names that are common names and not technical names. Like for instance, if I have a benzene substituted with a methoxy group, right? The benzene is not the parent. We just call this compound anisole. Right. If I there's also another compound. Like if I put an amine here, then the benzene parent is not a part of the name. We just call it aniline. All right, so there's a couple a couple of compounds where the parent name is not listed, right? It goes by a common name. So anisole, aniline. Um, there's also, if I put a methyl group there, then instead of being methylbenzene, it's called toluene. Right. So those are some common names. Now, what happens when you stick a second substituent on? It's shown right here, right? So this is will be an example of a what we call a disubstituted benzene, right? And so the key to naming the disubstituted rings is to know what the name of each position is. So you have what's called the ortho position, the para position, and the meta position. When it's disubstituted, there's no numbers. Right? You're either going to use a O, a P, or M. Right? So so ortho is the same as something that's 1,2 disubstituted. You see the two groups are right next to each other. And then meta is it's like a 1,3 disubstituted benzene. And then para is 1,4. But you don't use the numbers, you use the name, right? Ortho, meta, or para. All right. Any questions about that? So
is there a video for this?
For naming?
Yeah.
No.
All right.
All right. So for but it's in the chapter though. If you look at the syllabus, the section on aromatics, it has a reference to the chapter in the book on nomenclature.
Okay.
Yeah. All right. So here, let's just talk about the nomenclature. Right. So this compound right here, you can see that the methoxy group and the chlorine are 1 and 2 next to one another. And so this could be, you could call this, there are two ways to name it, but normally how we do it is we the parent, we give it, we use alphabetical order, right? Because this could be orthomethoxychlorobenzene or orthochloroanisole. So anisole, A comes before B, so that's why we chose anisole as the parent. So the ortho means that the groups are in a 1-2 position. The chloro, right, means that there's a chlorine at the ortho position, and then the anisole is the parent. And that's this compound right here. Right, the benzene ring with a methoxy group attached to it. Right, and it's the same for metachloroanisole. Meta means that the chlorine and the methoxy are in a 1-3 relationship, and then the anisole is the parent. And then the chloro tells you that there's a chlorine on there, and the meta part tells you where the chlorine is. It's at the 3 position relative to at the 3 position relative to the methoxy group. All right, and then the same thing with the with para. It's the same protocol, right? The para means that the groups are 1-4. So if I were to draw para chloroanisole, it would look like this. Like that. Right, where the chlorine is at the 4 position, and then the methoxy group is at the 1 position. Any questions about that? So let's go down to the next section. But before we start talking about the reactions, I want to see if we can name a couple of these compounds. Right. So let's look at this compound right here. How would you name that? Right. The parent is going to be anisole. Is that right?
Would it be orthobromoanisole or something?
Yes. And to abbreviate ortho, you can just write a lowercase o. Right. So it's orthobromoanisole. What about the other compound here?
That one is para-bromoanisole.
Yeah, para-bromoanisole. That's exactly right. All right. What about this compound? How would you name that? Is it ortho or meta?
Meta.
It's meta, right? Because the groups are in a 1-3 relationship. So 1, 2, 3. Now we got 2 choices. It can be nitrobenzene or bromobenzene. Which parent would you choose?
Bromo because of ABC order.
It's alphabetical order, right? So this is going to be meta nitro benzene. And nitro is not. Let me rewrite that. All right, is that okay?
Dr. Russell, could you explain how we chose the parent one more time?
The parent is, what did I say? Nitro. Oh, my bad. I left off part of the parent. It should be bromobenzene. So the parent is going to be based on alphabetical order, right? So it's the parent is going to be benzene, right? But it can be bromobenzene or nitrobenzene because you got 2 different substituents. So we chose bromobenzene as the parent because B comes before N in the alphabet.
Okay, thank you.
Hmm.
So the starting material has nothing to do with which is the parent.
Mm-mm. Not when you, because that's just for the reaction part. We just naming the product.
Okay.
Yeah. All right. So now let's look at the reactions that are happening. Right. So in the top reaction, right, I'm starting with anisole, and then I'm going to add. I'm doing a halogenation on it. Right. Anytime you do um, any type of substitution on a benzene ring that has a substituent, you're going to have that substituent is either going to be what you call a ortho para director or it's going to be a meta director. It depends on what type of substituent it is, right? If it's a donor, like the methoxy group, it's an electron donor, then it's going to be an ortho para director. What that means is that whatever you're adding to the ring, it can only go to the ortho position or the para position. It can't go into any other position. All right, so those are electron donors. So what's an example of a donor would be something that has lone pairs like this oxygen. Other donors are, so let me put this. So lone pairs are donors, alkyl groups. Anything that's electron rich can be a donor, right? Lone pairs, alkyl groups, other heteroatoms. Need more room for that. And by heteroatom, I mean something like, let's write it down here. Nitrogen, oxygen, basically atoms that have lone pairs. Sulfur, halogens. Right, halogens like chlorine, bromine, fluorine, all of your halogens are donors. Right, so you have anything that has lone pairs on it can be a donor, and then alkyl groups can also be donors. Right, so we look at the reaction, we see that the methoxy group is a heteroatom. Oxygen is a heteroatom. It's got lone pairs that it can donate into the ring, and so the outcome of the reaction is already fixed. We know that bromine, right, is going to go to the para position and to the ortho position. Because when we add Br2 to a aromatic ring in the presence of iron bromide, we get a bromine added to the ring. Right? Questions about that? This is sometimes it trips people up because of the definition of what a donor is and what a acceptor is, or an electron withdrawing group. So, are there any questions about that?
So does it make both the ortho and the para, or does it choose one?
Well, you make both, right? But normally the para is the major product. That's a good question, right? You make both compounds, but the para is major. Why do you think that is? It's
Uh, the substituent groups are further away from each
further
other.
apart. It's sterics. The groups are further apart from one another, and so that kind of drives which product is favored, right? So sterics kind of controls that. So the para product is major, and then the ortho product is normally minor.